Hello everyone, my name is Gargi and I'm going to be talking about how printing floating point numbers is surprisingly hard. So this is a problem that many of us have probably encountered. So let's say you have a Python REPL and you write 0.1 in the Python REPL and you get 0.1 as back on the screen, and then you write 0.2 and then you get 0.2 back on the screen. But when you add 0.1 and 0.2, you get 0.3, a whole bunch of zeros and 4. And it's kind of surprising that even in 2020, like, the computer can add 0.1 and 0.2 right, because I mean it's pretty obvious that the answer should be 0.3. And this surprised me, and I wanted to dig more into why the computer can do this correctly. And this is not just with Python. If you go to like OCaml REPL or Haskell REPL or like even JavaScript REPL, you will still see this. So why is that? So one of the first things that we should talk about is floating point numbers before we talk about the algorithms. So humans love decimal, right? Because that's how we learn to count. And if you have, let's say, 0.25 as the number, then you can represent it as 25 into 10 raised to the power 2, 10 raised to the power minus 2 as the decimal representation. And computers love binary. So if you have 0.25, then you can write 1 into 2 raised to the power minus 2. And that's the kind of that's how you can kind of represent it in the binary. And the cool thing is that decimal to binary conversion is simple for integers, so because there's a limited range, but decimal to binary for floating point numbers is one-way compatibility. So all binary floating point numbers, all binary floating point representations have a corresponding decimal equivalent, but not all decimal floating point numbers have a binary equivalent. So for example, if I were to represent 0.3 as the IEEE 754 floating point standard, where I have a sign bit, I have a few bits reserved for exponent and a few bits reserved for the mantissa, and then I use this formula to convert it back to decimal, then even though like the binary representation is for 0.3, what I get back is 0.30048828125. And while like this precision may increase, like the given like how many bits you used to represent the exponent in the mantissa, because there's a one-way compatibility, you can't get back exactly 0.3 from a binary representation. And that's where like the floating point algorithms come in, or the printing floating point algorithms come in, and their job is to figure out that when you have a floating point number, which like how should it be printed. So the other surprising thing is like the first time an algorithm came out to print floating point numbers is 1990. Like computers had been around for decades by that point. So the first algorithm was called Dragon 4 by Steele and White, and one of the big things that this paper did was like first not only establish the state of the art for printing floating point algorithms, but it gave us like these 4 criterion for printing floating point algorithms. Is like first, information preservation. So like if you print a decimal number, and then if you read back the decimal number that was printed, then you should get the same result. It's minimum length. So if you have a floating point number and you're printing a floating point number, then print the minimum length of the floating point number while still preserving information. It's correctly rounded according to the floating point standards, and the number that's generated is generated from left to right. And one of the completely useless facts about printing floating point algorithms is that they're all, like, all the popular algorithms are based off of dragon names, and the first one was called Dragon 4 because there's something called a dragon curve, which you can make from paper by repetitively folding it and when you fold it, there's folds and there's peaks and folds and peaks, and the initials are F and P, which are also the initials for floating point. So, and that's why it's called dragon algorithm. So how Dragon 4 works is that for one decimal number, there's an entire range. For one binary representation, there's an entire range that maps back to. For one decimal range, there's an entire range that maps back to one. For one binary representation, there's an entire decimal range that maps to that one binary representation. So in this range, what we will do is we will go through this entire range and then figure out what is the shortest number to print in this range. So Dragon 4, quite literally, if you think of it like as a brush going across the line, it literally makes a pass through this entire range and figures out what's the shortest number to print in this range is. And the cool thing about this algorithm is that it's correct 100% of the time, and but the caveat is that it uses big integer arithmetic. So you have machine integers and you have big integers, which are like numbers represented in software and not in the hardware. So because of that, it's relatively slow. The next algorithm to come around was in 2013, so almost 20 years after, more than 20 years after Dragon 4 came around. So when the first time in 1990 the Dragon 4 came around, people were like, yes, this is it, and all the programming languages started using Dragon 4, and it wasn't until 2013 that a new algorithm came around, and it was by Leucht, called Crochet III. So Crochet, if I'm right, it was a cartoon. It was a dragon in a French cartoon, and if you think of Dragon 4 as like a brush sweeping through, as like a wide brush sweeping through this range, Crochet is as a small brush which is sweeping through this range, checking all the numbers one at a time. You can think Crochet as like a broader brush sweeping through this range. But what happens when you have a broader brush is, like, when you get to the ends, it becomes quite bloody. Like, you may sweep more area than you intend to. So what happens with the sweeping of the brush is that Crochet will for sure brush in between the numbers A and B, but it might go outside the numbers. The range might go outside the numbers A and B. So one thing Crochet does is, like, it does the narrow approximation, and then there's a wide approximation. So if the narrow and the wide approximation match, and you find the numbers within the narrow, and you find the shortest number within this narrow approximation, then you go ahead with the narrow approximation. But if there's an uncovered interval that is there in that is found in this, then you reject this, and what happens is Crochet is correct 99.5% of the times, but the 0.5% of the times when you have to reject the output from Crochet, the algorithm falls back to Dragon 4. So the good news is it's 12.5 times faster than Dragon 4, and it does not use arbitrary integer arithmetic anymore. It uses machine integers, so 64-bit machine integers, and it's correct 99.5% of the time, and the rest of the times when it's not correct, it uses Dragon 4 as the fallback. So JavaScript and Rust use Crochet 3 for printing floating point algorithms. And the last algorithm I'm going to be talking about is Ryu, which is a Japanese, I think it's a dragon in one of the Japanese animated shows, and it's by Adams, and it came around 2 years ago, so it's really cool that advances in printing floating point numbers are still happening. There's still a lot of scope for improvement. So let's say like you want to print 0.3, and like these are the numbers that map to the range in 0.3. We still care about like the four criteria that were put forth by Dragon 4 were information preservation, minimum length, correctly rounded, and left to right generation. But this algorithm is not doing generation anymore, so we still care about the other three criterion. And how Ryu works is that it keeps cutting off digits, and it doesn't cut them one at a time, but it cuts as many digits as it can in one go. And then it looks at the numbers after each pass of cutting to see, is this the shortest number that you can have? And then what number looks like, out of all the numbers that you are cutting digits off, which number looks like the upper bound, and then rounds them off according to the IEEE standard, and that's the result. So Ryu only uses integer operation, and it skips as many digits as possible, and it's three times faster than Crochet 3, which is so cool. Yeah. So in conclusion, advances are still happening for something that was thought to be like a solved problem, and one of the challenges is that there are two problems here. One is the input problem, which is like what floating point number are you giving to the algorithm, and the other is the output problem. It's like what you are getting out of the, or what you're printing from the floating point number that you get. So all the papers only focus on the output problem, and all the algorithms only focus on the output problem and not the input problem, and that's something they assumed is solved for them, which might not be the case. And yeah, that's it. Thank you so much.